Tell me. It's maybe a little early, right? Or
we can start.
We can start?
Sure.
Okay, very well. So, okay, so what did we do last time? So last time we took a look at the first algorithm, let's say, in convex integration that Laszlo and I introduced to prove the existence of bounded weak solutions of the Euler equations, which obviously cannot conserve the energy because they're zero at some past time, zero at some future time, and they are non-trivial at some intermediate time. Okay. So now the idea of these lectures is to move towards a proof that there are continuous solutions which do something similar. So we will focus actually on violating the kinetic energy rather than being compactly supported. So you can do that too. Okay. But before getting to that, so that will be again some other algorithm which will look closer to the constructive algorithm that we saw actually last time, rather than to the functional analytic argument. It's actually a quite interesting theoretical problem. So for the more sophisticated arguments, we do not know of some functional analytic approach which does not have to go through some sort of detail on how you construct this sequence, like, you know, one after the other. And it's a very interesting question. But before actually we go into that, we want to see a precursor of what we introduced for producing continuous solutions of the Euler equations. And this precursor is the famous Nash Kuiper C1 isometric embedding theorem. And as for the previous lecture, I'm actually following a precise reference. And the precise reference is Nash's original paper. But I have written an interesting, say, simpler or more modern rendering of Nash article. In this long article that I wrote, or long piece of the book that I wrote when Nash actually got the Abel Prize. So it's called The Masterpieces of John Nash. You can think about it as a set of lecture notes on Nash's 1, 2, 3, 4 most famous papers. And one of them is actually 5 most famous papers. And the second one is about the isometric embedding problem. Okay, so what is the isometric embedding problem? So I'm not going to kind of focus too much on geometry. So let me assume that we are some omega little patch of some manifold, but let me think really that I'm actually inside an open set inside the Euclidean space. Okay, and on this open set, I am given a Riemannian metric Gij. So what is this Riemannian metric? So this is just a family of symmetric matrices which depends on the point X. So a symmetric matrix field, right? So you have to think Gij simply goes to omega into the space of symmetric matrices n times n. Okay, positive definite. Okay, and assume it's smooth. Okay, so this is a Riemannian metric, and as you might be familiar with, we understand the length of curves inside this Riemannian metric. So the length of a curve gamma, where gamma is some map which is going from, say, the interval 0, 1, for instance, into your omega. So we understand the length of this curve with respect to the metric G to be equal to the integral between, say, 0 and 1 in this case, so of the square root. And then here, by using Einstein's summation convention, you have Gij gamma of t, gamma dot I of t, gamma dot j of t. Maybe it's more consistent to actually write it in this way, dt. So what I'm doing over here, I'm simply measuring the modulus of the velocity vector according to this metric, right? So which gives me a symmetric quadratic form. Okay, so now the question of whether you can actually embed isometrically this Riemannian manifold into a higher dimensional space is the following. So you are looking whether there is some map U which is going from omega into Rn. Now this is a big Euclidean space. And what you want to know is whether the length in your original manifold of any curve gamma is going to be equal to the length in the Euclidean space of the image of gamma through your map U, okay? So now this U composed with gamma is a non-X curve in the Euclidean space. And so what you're actually trying to see is that if this one is really equal to the integral between, say, 0 and 1 of really the modulus of the vector gamma dot, the modulus of the vector U composed with gamma dot of t dt, okay? So if you carry on the computation, so this is a very simple exercise, okay? So what is actually U composed gamma dot of t? Okay, so this is going to look like this. So it's going to be the square root, and now let me just write it in the following way. So gamma dot of t dot du transpose of gamma of t dot g of gamma of t dot du of gamma of t dot gamma dot of t. Okay? So, sorry, there's no intermediate, there is no intermediate element. Okay? So this is a very simple computation which essentially just follows the chain rule, right? So you differentiate this guy, and of course if you differentiate this guy, you just discover that you have this. Right? And somehow when you're making a scalar multiplication of two vectors, you can understand it as the multiplication of the two matrices that you get with the vector and sort of the transpose of the other vector. And that's how you get this formula. So you transpose this, and then when you transpose this, you get the transposition of gamma dot times the transposition of du. And now you want actually this length to be equal to that length, which is to be equal to this formula. But you see, it's, you're choosing arbitrarily gamma, right? So I can really stick any gamma I want over there. And so it's a simple exercise to see that for this formula to be valid for every gamma, you need, so let me maybe put over here this as a lemma. So if U is in C1, right? So this identity true for every gamma. So for U in C1, the identity LG of gamma is equal to LE of U composed gamma, holds for every gamma, say C1 curve, if and only if you just have that G, so that du solves the following elliptic PD, the following PD. So if and only if du transpose times du is equal to G. Okay, so it should remind you something, it should remind you of something which was instrumental in the second lecture, right? Modulus of U prime equal 1. It looks very similar to that, right? It's like a matrix version of that particular equation, if you want, okay? So it has a lot of similarities to the iconal equation. Okay, so this is the dilemma. So finding an isometric embedding is equivalent to find an injective solution of this nonlinear partial differential equation, which is C1, okay? Now, it's a little bit annoying to check whether something is injective or not, but just notice the following. Because you have this relation, and because G is positive definite, this relation implies immediately that the derivative of U has to have full rank, okay? So it has to be at least an immersion. So locally, on a sufficiently small patch, it has to be kind of injective. The only thing that might happen is that the image is kind of going to self-intersect itself, okay? And we're going to forget about that. I mean, we're going to sweep it under the rug. You can just take somehow like the notes and you can see how you deal actually with that, which is more like an annoying technicality in a sense for us at the moment. So what we really want to do is, because we are PDE folks, forget about the geometry. We want to solve this PDE and finding C1 solution of this PDE. That's all we want to do. Yes, and the global injectivity, exactly. So to get global injectivity, I mean, I will give you a proof of the existence of, solutions of that PDE, which then will be automatically locally injective without having to do anything else than studying the PDE, okay? And then to get global injectivity, you have to solve a more global property, right? And it's no secret that when you start having more global problems, it's actually getting closer to geometry rather than analysis. So I will just essentially ignore that issue. That's what I will do, okay? So instead of proving the existence of isometric embedding, I will prove the existence of isometric immersions. Okay, and I will prove this theorem. And this is the theorem of Nash in its original form, except Nash states it for a general manifold, and I will just, stick to some portion of the Euclidean space, so some chart, some open disk. And Nash also deals with the embedding problem, and I will not deal with the embedding problem, just with the C1 isometry. Okay? But, so the theorem of Nash says, assume V from omega into Rn is a C1 immersion, which is short. And short means, so now let me introduce a little, I mean, we still love the geometries. So let's still introduce a little bit of geometry notation. So this one is often called the pullback of the Euclidean metric in your manifold, okay? And the geometries have some notation for them. So this is what is the pullback. And then the Euclidean metric is the standard metric. I have to give a name, right? But it's essentially just getting in the Euclidean space the matrix G, which is identically equal to the identity matrix, the delta ij, okay? So let me call it E for Euclidean, okay? So the thing that I want to solve is U, so the pullback of the metric, so U sharp E equal G. And now being short means that instead of having that PDE, you have a strict inequality over here. A strict inequality in which sense? In the sense of quadratic forms. So now if you think about it, why do you call it short? Because you see, if I have an inequality in the sense of quadratic forms, it means that instead of having the identity that this guy is equal to kind of the length in the Riemannian setting, right? So once I have actually this identity over here, that identity, what really happens is that the integrand that you have over here is equal to the integrand that you have over there, right? And now what is actually happening is that if I take a strict inequality, the integrand is always strictly less than the other one. So instead of having the property that each curve is mapped into a curve of equal length, actually each curve is mapped into a curve or shorter length. And that's why we call them short map. So if you have a short C1 isometric immersion, and big N is bigger or equal than M plus 2, okay? So the Euclidean space in which I'm going to put my manifold has, that, I mean, the image is going to have codimension 2 or higher, okay? So then, for every epsilon bigger than 0, we will construct U, C1, isometric immersion. And so isometric immersion now means that I really have a solution of the PDE. Okay? With the property that my new solution is away from the previous solution by epsilon, uniformly in the C0 norm. Okay? In the uniform model. So, just remarks. 3 remarks. So, Nash deals with general manifolds. With some assumptions. For instance, you can take compact manifolds, compact or closed manifolds. Nash deals with embedding. And the actual statement of Nash after this is that if V, you know, it's globally injective, so it's an embedding, not only an immersion, then you will be able to construct U that it is also an embedding. Okay? And then finally, Kuiper does the case of big N equal M plus 1. Okay? So now, this theorem was sort of terrifying for the geometers of the time, or even for the mathematicians of the time, because think about this, right? So take the round sphere of radius 1. That's a Riemannian manifold, okay? Now, any map which is going to take this round sphere and shrinks it into a ball of radius, I don't know, a sphere of radius 1/1,000,000 is a short map. It's a very short map, right? And now Nash-Kuiper theorem is telling you nearby, take epsilon 1,000,000, so nearby in the ball of radius 2/1,000,000, there is a perturbation of this, which is going to be an isometric embedding. So meaning that I've actually squeezed my sphere of radius 1 inside a very small ball of radius 2/1,000,000. C1, smooth, I mean, not creating kinks, right? Because I could actually start with the sphere, which is sort of smooth, and kind of smash, for instance, the upper cap, and like, you know, create a discontinuity and still keep like, you know, the two pieces kind of isometric. And I can sort of continue smashing, or as you would actually like in India as a joke, so make, you know, your sphere of paper. So this is actually Gromov. Make your sphere simply made of paper or some other thing, and call an elephant to actually go on top of it. And squish it into something very small, okay? But Nash is actually doing this, keeping C1, not like, you know, crunching your paper. And it's an important remark. It's impossible to do it if you were C2. So it's not going to be relevant for our discussion, but I still want to think about it. And so fill in the details of the following exercise. Okay? So take U from, say, the standard sphere into R3, which is a C2 isometric embedding. Actually, make it C3, which makes it easier. And then think about it's also true in C2, but it's harder, okay? When you can differentiate 3 times, it's going to be easier. Okay, so take this, which is an isometric embedding. Okay, then make the following consideration. So take a point P, which is in U of S2. Okay, so here you have your image, say, U of S2. Okay, take a tangent plane over here. Right, so assume this point P, I mean, you can translate and rotate your surface, right? So assume P is the origin, and assume the tangent space to P at U of S2 is the horizontal plane, okay? So it's the plane x3 equals 0, okay? Locally, this let me call this surface gamma. So locally, gamma is the graph of a function g. Okay, because, well, g is already the metric. Let me call it a function f. Okay. Recall Gauss theorem. So recall Gauss theorem. So the Gauss curvature, which is the determinant of the second fundamental form of your surface. And here is where the smoothness somehow enters, right? I mean, because the graph is sufficiently smooth, I can compute the second fundamental form. So this one has to be the Gauss curvature of your sort of intrinsic manifold, which is equal to 1. Okay? Now compute A in terms of the second derivative of f. A is not the second derivative of f, it's the second derivative of f exactly at the tangent point, but it's the second derivative of f times something. Okay, make the computation. But what we will conclude from this is that the determinant of the second derivative of f is positive. And you see, if the determinant of the second derivative, you are a 2 by 2 matrix, right? Which is symmetric. You diagonalize and you get the eigenvalue. Either both eigenvalues are positive or both eigenvalues are negative, which means that either the function is locally convex or it is locally concave. And once you've actually done this exercise, conclude that U of S2 is either convex or concave. Well, it cannot be concave, right? I mean, it has to be convex. So it's a convex body, or it's a convex surface. Yeah, I mean, the concavity or convexity of the function f depends on whether, like, you know, your surface is lying down compared to your tangent space, or it's kind of lying up, right? If you put it in the way I've put it in this picture, the only possibility is that it is a convex function, right? Because it has to be above. Okay, of course, a convex surface now, because you are in isometric embedding, you have a convex surface which has area, the same area as the unit sphere, which is 4 pi. There is no way you can actually put it in a ball of radius epsilon, okay? Because the projection from the sphere of radius epsilon onto your surface would be a map which is area decreasing, okay? And so you would project and decrease, like, you know, get somehow that the total surface has less area. So what is the point? So, you know, this is no contradiction to the theorem of Nash, or Kuiper, actually, because Nash does it in codimension 2 and leaves the codimension 1 as an exercise. Somewhat more difficult than usual, so. So there is no contradiction because this guy is C1, okay? And so I hope you start feeling kind of that there is a similar, like, you know, parallel with the Euler equations, because we have, I will claim that we have C0 solutions that do not conserve the energy. And then we have a computation which tells you that if we have C1 solutions, then the energies are conserved. So here you see something similar. In a sense, you see in the isometric embedding problem, if you are a C2 surface, you can make sense of Gauss theorem, okay? But if you don't have enough regularity, you're essentially not able to make sense of Gauss theorem, and so therefore you cannot actually draw this conclusion, and the conclusion is even false, okay? Okay, very well. So now we focus on proving this theorem. And then again, another analogy with the iconal equation. So if you remember, in the iconal equation, what did we do? We started from a solution, I mean a sub-solution, something which had an inequality, and then we constructed somehow our solution by making infinitely many perturbations from it, right? I mean, this was kind of the method that we essentially will be calling convex integration, the one which builds the subsequence explicitly. I mean, not the one which is abstract. I mean, I started, if you remember the proof, I started with 0, but, you know, I could have started anywhere with something which had modulus of the gradient less than 1, right? Because we had an algorithm to perturb any such function a little bit in such a way that you got actually closer to have the modulus of the gradient equal to 1. And this is what we will do over here as well, okay? And again, it's no kind of, it's no coincidence that we need to start with something which has an inequality of this kind. If I had the opposite inequality, I wouldn't be able to deform actually my solution easily in such a way that I can sort of decrease the length. So we will see in a minute that the kind of perturbations that we sort of give naturally are length increasing, okay? So let's see how I'm faring. Yes? No. So this will be sort of like then further coming. So there is a similar question, which is a question which is posed by a Russian mathematician, Borisov, back in the 50s, and which is taken again by Gromov later in the 80s, which asks, okay, what is kind of the threshold Hoelder regularity for which you will have some sort of rigidity like the one over there, or some sort of flexibility like the one over there. And so what we will do, we will discuss what you can do actually in the isometric embedding problem towards the end of my lecture. But unlike the Onsager conjecture, which is completely solved on the Hoelder category, the problem of Borisov and Gromov is not. So it's still open. So there is no proof which gives you kind of, there is no proof that gives you an optimal threshold. And there is a conjecture, and the conjecture by Borisov and Gromov is that in codimension 1, as you go higher in the codimension, you can push actually the Hoelder exponent higher and higher. In codimension 1, the conjecture is that C1 1/2 is the threshold. And we don't know the C1 1/2, neither from above. So the rigidity arguments that we have are for C1 2/3, neither from below. So the best theorem that we have is for surfaces in R3 is C1 1/5. So there's a big gap between the conjecture and the proof. But is the preprint online? Is the preprint online? The one of Jonas and Dominic, you mean? They have a quarter? They have a quarter? I don't think so. I mean, I know that Jonas and Dominic are actually working since long at trying to do this C1 1/3, and they don't have the preprint out yet. Yeah, check. I think it's C1 1/5 is still the record currently. But yeah, so Jonas and Dominic announced to me C1 1/3, but I don't think they have written any detail at the moment. And this is what I also asked last time. Like, it's not here. Okay, check it out. I think it's still 1/5. Okay. Very well. So we want to actually produce okay, and it's very important. We are not going to prove Kuiper improvement. We are really going to prove Nash original one. So I will be in codimension 2. Okay, so it's somewhat harder, not much harder, but it's somewhat harder and more annoying to actually do it in codimension 1. Okay, so I have my V over here. This I think of it as V0, and the goal is to produce from, say, V0 a new map V1 and a new map V2 and so on. Right, and in each of the steps, I am kind of doing the following. So I am going to call this guy over here the metric error. Okay, G minus V sharp E is going to be the metric error. So let me say H is going to be something like G minus VK. And actually, let me call it VQ. the element of the sequence. So this one is the metric error, okay? And the goal is produce VQ plus 1 so that I can keep actually doing the same mechanism. And to keep doing the same mechanism, I need to have the same inequality over here. So such that, so VQ plus 1 is going to be less than the metric error. Sorry, it's going to be less than, okay, so VQ plus 1 sharp E is going to be less than G, so that I can define a new metric error. Maybe this one I call HQ. So that's one important point. Okay, the second important point is that VQ plus 1 minus VQ in C0 norm is small. And by small, I really need smaller than some elements of a series that I will resum. And once I resum the series, I'm just going to discover that the distance from, like, the initial guy that I started with and the eventual limit is less than epsilon. So it has to be a series which sums to epsilon, okay? And I also want the C1 norm to be under control. I also want this one small. But this I will not be able to make too small. I will make it small enough at each step in such a way that I can again sum the series, and I can actually say that I have a convergent series in C1, okay? So that's what I want to do. So this one is going to be small, and this one is going to be extremely small. Oh yes, C1, yes. Or, if you want, since I have already the C0 norm, what I really care about is the difference between the two derivatives, okay? Okay, so now enters what is called Nash spiral. Okay, what is a Nash spiral is a first perturbation that we will engineer to understand what happens, what we can try to do to produce this VQ plus 1. Okay, so the Nash spiral looks like this. So you take VQ plus 1 at a point x, and you add VQ of x. You take VQ of x, and then you add the following. So you take, so at each point, you have to imagine you have your point here, UQ of x. So I'm imagining at the image. And then because this one is an immersion, okay? Because this one is an immersion, there is a tangent space to the immersion. So the UQ of x, okay? Now, again, to avoid an annoying problem, put actually the codimension to be exactly 2. If the codimension is exactly 2, you can choose 2 vector fields which are normal to it, okay? If the codimension is higher, you have many ways of choosing 2 vector fields which are normal. But as it happens somehow often, we see, for instance, this one in democracy, when we have too much choice, it's more difficult to make a choice. So just imagine you are in codimension 2, and then you have 2 normal vector fields, which of course I cannot draw on the blackboard, right? So let me draw them like this way, right? B and N. Okay, B and N have the following properties. So they are normal to each other. Of course, they have modulus 1. And they are normal to the tangent space, right? And the tangent space is, okay, let me call it the tangent space. Okay, so now here's the perturbation that I'm ending. So I'm ending, so 1 over lambda, and I will call, okay, let me call it 1 over lambda for the moment. So I will add 1 over lambda, n of x, and then sine of lambda, and then I'm going to have a one-dimensional oscillation. It should remind you of the one-dimensional oscillations that we added to actually get a kind of slope from below 1 to above 1 in the iconal equation. So I'm going to add the scalar product of xi dot x. What is this xi? This xi is just some fixed direction in your omega, in your kind of parameter space. Okay? So this is one guy, and this is another guy. Okay, and now let's see what happens when I'm computing this VQ plus 1 pullback of E. What is this? So this is dVQ plus 1 transpose times dVQ plus 1. Okay? And so now I want to compute dVQ plus 1. And this is, of course, going to be dVQ. And then what do I have? Well, first of all, let me, you see, this lambda, this parameter lambda, will be shot to a very large number, as we did actually in the iteration like on Friday, okay? So first of all, I'm going to kind of think about what happens over here, right? So when I differentiate this guy, there's a lambda coming out and it cancels that one, right? And so I'm going to have something like this. So sine of whatever I have over there. And then I'm going to have n of x tensor xi. Okay? Then okay, sorry, that's cosine, right? Because I need to differentiate. Okay, then there is sine of whatever I have over here. And then b of x tensor xi. Okay, and then, okay, so this is going to be with a minus. Okay. Right. Let me also, I forgot a piece. So let me also say that I add something over here, which I will call the amplitude. Okay, let me put that over here too. And let me put this amplitude in front of everything. So it's the same amplitude for the two oscillations. Okay, so whatever I have, then I will call something like bgo of 1 over lambda, right? Because I'm not differentiating any of these guys. So I'm thinking about A, N, and B. N and B are fixed. A, I will fix them in a moment. But here there's this lambda which is actually moving. So here there's something which depends on everything, but as I shoot lambda to infinity, it goes to 0 like 1 over lambda, okay? And now, when you compute this thing over here, so what do you have? So the initial metric, obviously. And then all the cross terms, right? So I have to start making all the products of transpose of these pieces times themselves, right? So, okay, so let me say, first I have so there is this guy, I mean, there is the one which is coming from here, and the one which is coming from here is going to have the transpose of this, right? And just simply remember the following very simple fact. If I have, say, E, well, okay, let me call it this way, I don't know, alpha tensor beta, right, times gamma tensor delta. This is going to be the scalar product between beta and gamma and alpha tensor delta, okay? So when I multiply this guy by its transpose is going to be xi tensor n, and when I scalar multiply n with itself is going to have modulus 1, right? Because n scalar product with n is equal to 1. So what I find over here is a squared cos squared xi tensor xi. Okay, that's one non-mixed term, and then I have b squared sine squared xi tensor xi. And now I want to actually discuss the cross terms. And the reason why, for instance, there is no cross term over here, it's because n and b are orthogonal. So when I'm going to have n of x tensor psi times the transpose of this, I will see the scalar product between b and n in that formula. Sorry? You have to speak louder. I have not understood the question. Oh, yeah, a squared, yes, sorry. Yes. Very important point, actually. Yes, b disappeared because the modulus of b is equal to 1. Thank you. Okay, so this cross term is not there because b and n are orthogonal. And these cross terms are not there either. And the reason is because the orthogonality between, for instance, n and the tangent space, so this orthogonality over here, what it really means, it means that bx transpose times the u q of x is equal to 0, and nx transpose times du q of x is equal to 0. That is what the orthogonality means when you actually go into the formulas, okay? And so there's not going to be any cross terms over here. So this is exact, and then whatever is left is big O of 1 over lambda. Okay? Now I can actually sum these two guys, right? And because cos squared plus sine squared is equal to 1, what I actually discover is that I have d vu q transpose times d vu q plus a squared psi tensor psi. Okay? Did you find out whether? Surfaces in R4. Okay. I'm talking about surfaces in R3. So surfaces in R3, 1 over 5 is still the best exponent. Currently. And they are trying to beat it as we speak. Yes. Okay, plus big O of 1 over lambda. Okay, what happened at my metric, right? Well, think about this, right? Like at the particular point where I am, I could in principle diagonalize the metric, right? And so I have the metrics on the diagonal. And I could choose actually xi tensor xi to be the, xi to be one of the eigenvector, right? So for instance, the one that is sitting on the top of my matrix, right? And so I have increased my metric by adding actually a function to my choice to one of the diagonal entries, okay? And if it stands to reason that if I do this a finite number of times, for instance, on that particular point, I can simply fill all of the diagonals. And if my error, if my a squared is almost the ground that I have to cover, I actually got that this bq plus 1 sharp e is almost equal to g at that point. Not exactly, because of course I still have this error over here, right? But I can make this error as small as I want. Okay? So here's the idea. But you have to be a little bit more careful about it. And a little bit more careful about it has to do with the following. I can put a diagonalization of the matrix at that particular point. But nearby, maybe I'm not diagonalizing the matrix anymore, right? Now, some of you could just say like, oh, well, yeah, I could do it. I could actually make my metric conformal. Yeah, for instance, for two-dimensional surfaces. But in general, you're not going to be able to do. So you need to be a little bit more clever. And people talked about, in the past week, about this geometric lemma, and there's, the geometric lemma over there, and the geometric lemma here, and so on. And I think they all refer to the fact that I would show you the geometric lemmas. So here I'm going to show you the first geometric lemma. Okay. And I'm first of all going to show you a baby version of the geometric lemma. Okay, so there exists direction psi1 psi m times m plus 1 divided by 2, the space of symmetric matrices, the dimension of the space of symmetric m times n matrices, and functions a1 x am times m plus 1 divided by 2 from the space of symmetric matrices bigger than 0 into R, smooth, with the following properties, or with the following property. Okay, so for every h, which is in a ball of radius C0 next to the identity, remember the identity for us is kind of the Euclidean metric. So it's really like, the matrix which is all ones on the diagonal and then all 0. This one is a dimensional constant, so maybe I should say that exists, C0 bigger than 0. Okay, such that so for every h, so h is going to be the sum for I equal 1 to m times m plus 1 divided by 2 of ai of h squared psi I tensor psi I. Okay? So, yes? Yes. Sorry, with the following property. For every, we have, sorry, the such that is actually, should have been before, but I already said with the following property. Yes. The statement is, for every h in there, I'm actually going to be able to write h as a convex combination. I mean, it's not a convex combination, right? It's a linear combination, but I'm taking kind of the square over here. So it's a little bit like AI, I would like to be the square root of, my linear combination, okay? So now proof, quote unquote, because I'm going to leave actually a lot to you, but it's all elementary, okay? So first of all, how would I actually try to do this? So I would try to do this by, first of all, taking psi I of the correct number, which is the dimension of the space of symmetric matrices. And then if I have linearly independent tensors like psi I, tensor psi I, so check that you can actually choose them so that they're linearly independent. Every symmetric matrix is going to be a linear combination. And so in a sense, I know what is the AI squared, right? I mean, there's no choice. It's just some linear function of H. Now, to define my AI, I want to be able to take the square root. And of course, I need them to be positive. And as long as, in this region, they are going to be positive and a little bit bounded away from 0, the square root will still be smooth, right? Just to be uniformly bounded away from 0. So I need actually to write it as, a positive linear combination of these guys, okay? So when would that actually happen? See, assume over here that I'm going to add also a fake number, which is going to be a m times m plus 1 divided by 2 squared times 0. So if, you see, these m times m plus 1 divided by 2 points and 0, they actually span a simplex, right? I mean, like, the generalization of a square. So they span a simplex with some open set inside, right? So if my simplex over here, right, for instance, gets the identity inside, if it gets the identity inside, then in a neighborhood, my combination over here is going to be a convex combination, made all of positive numbers. I throw away the 0, and I get positive numbers for the AIs over here, and then I take the square, and I find my functions, and I'm done. So now it seems you've got to sort of find this simplex, which contains the identity. But in fact, there's a very simple geometric observation. So pick them to be kind of, linearly independent. So it certainly contains some matrix B here in the interior, which is not the identity. Okay, but if I apply a transformation of the following type, so if I map H, so if I map, say, B into A transpose times B times A, all I'm claiming is that I'm able to find a linear transformation of Rn in such a way that B really gets mapped into the identity. And this you should know from linear algebra, because the existence of that map is simply saying that you can always take a quadratic form into its canonical form. And its canonical form depends on the signature, and the signature of my quadratic form is all 1. So there's only one guy, which is all of the identities, if you up to similarity of Rn. And now you simply realize the following, that if your psi I didn't contain the identity in the interior of the simplex, I find a point in the interior, I apply this transformation map, and then I apply the transformation map to psi I, which is psi I is mapped to A psi I. Okay? And then I'm done. Okay, very well. So you see, I can only kind of, do this in a neighborhood of the identity. That's somehow not very satisfactory, but of course, because of this transformation invariance, you can actually do that in the neighborhood of any positive definite matrix. And then in principle, you can patch everything with a large partition of unity and find your functions on a very large space, okay? So you can try to do the following exercise by using partition of unity. Oops. Oh, this is much better than the other one. I should actually always use this. So this is kind of the bigger version of the geometric lemma. So it's a corollary, which I give you by exercise. So assume gamma in the space of symmetric matrices, positive, is a compact set. Okay. Then there exists some number n, which is, depending on gamma, because I will need to cover gamma with all of these simplices that we found. So there exists n of gamma and directions psi1, psi-n, and functions a1, an, c infinity, on gamma, such that h is equal to the sum for I equal 1 to n of ai squared, and then I have psi I tensor psi I for every h in gamma. Okay? So now go back to your map VQ. Instead of doing this perturbation only once, find the psi1, psi-n vectors, adjust somehow each of the, okay, find the psi-i, find the ai squared, of course, and then adjust your metric sort of direction by direction until you reach VQ plus 1, okay? Type plus an error which is very small. And the very small error depends on the fact that I'm choosing these guys smaller and smaller. It's a recursive process, right? I mean, I have to, I will have to use a lambda 1, and then, I get a new map, and then I have to use a lambda 2, and then I get a new map, because each time I'm adding actually one perturbation at a time. But I have to do this finitely many times, and, do it as the time which is required. And then you get somehow your metric, which is almost the correct metric, plus an error. But remember, you don't want to be above the metric. So instead of shooting to be exactly the metric, shoot to be a little bit shorter so that the error doesn't push you over the metric. Okay? So that's what I want to do. Now, there's something a little bit annoying that I don't know how many of these guys I'm using, right? I might be using like a billion, a bazillion. And you might imagine that I don't want to do that. So, since essentially at the first step, when I start with V0, I can hit more or less the vicinity of whichever metric I want. Instead of hitting G, I hit G minus, the Euclidean metric times a small constant. And then I'm going to stay in the vicinity of it. And so the next metric error, instead of like lying in this gamma, I want it to lie in like, a neighborhood of the identity. I mean, not exactly a neighborhood of the identity, a neighborhood of the identity times a constant, okay, a fixed constant. So all I'm saying, of course, will make you believe immediately that, okay, I stated the lemma has to be true in here, right? But because the functions that I'm using are the square root of linear functions, the lemma is equally true if I take a cone, which is centered over here, okay? Only pay attention. I mean, it is true that it's equally true if I take the cone, but I'm taking a square root of something, so my differentiability degenerates as I get actually closer and closer to 0, okay? So the linear maps are smooth, but I'm taking the square root, so the square root are actually degenerating, okay? So, and this will be somewhat important later on. But so this means, at the first iteration, I need to add a lot of these spirals, but after the first iteration, I can actually engineer my modifications in such a way that each time, the next time, I'm actually putting the minimum number of spirals that I need. And the minimum number of spirals that I need is this m times m plus 1 divided by 2, okay? Because I will engineer my iteration in such a way that I'm always in this favorable neighborhood of the identity for my metric error, okay? Okay, why is this important? Because we got this, right? This we got. Now, let me first estimate. Okay, so this we got. And if I call this one guy HQ, right? So what I'm just telling you is that I can actually engineer that HQ is some number delta Q times the identity matrix plus a much smaller perturbation. Or, I can afford a constant somehow. I can afford this constant over here, this C0. So really what I want is something like this. That's all I want. Sorry, C0 delta Q. Okay, and this is up to me to choose, right? At each step, I choose how close I want to be. So this delta Q is kind of a parameter which for the moment is free. Okay, so let me check. What is going to be this VQ plus 1 minus VQ in C0? Well, look at the formula which I canceled, but maybe you took notes of, right? I mean, I had VQ plus 1 was VQ plus A divided by lambda, okay? So what is the size of the AIs of HQ, which I'm using in the formula? Right, there is this square root that I'm taking, and then they depend by our proof linearly on the error, right? So they're going to be less or equal than a constant. delta Q to the power 1/2. And how many of them I'm summing? Well, finitely many, right? And VQ plus 1 minus VQ in C0 is going to be less or equal than something like these coefficients, and then there was the 1 over lambda. But now the 1 over lambda I can really define, huge. So I can certainly engineer that this one is going to be less or equal than epsilon times 2 to the minus q. Okay?
Once you choose lambda to huge, but you need to also care about the regularity, right?
Right, that I will do later. So the C1 is completely solved. Then when I discuss the Hoelder exponent, I will try to be smarter. Yes. Yes. But so now what happens to dvq plus 1 minus dvq? Okay, so here we have the formula again. If I treat this guy as an error, right? Because I can make it as small as I want. Of course, usual is correct. If I want to try to get higher regularity than C1, then, it's not a good idea to take this one sloppy. But let's be sloppy. So let us take like this one really huge. If I take this one really huge, then the difference between dvq plus 1 and dvq is dictated by the size of these a's, right? Which is delta q to the 1/2. Okay, and now what should I do? Well, now I'm done. Okay, so I've chosen the lambdas in such a way that these guys are converging in C0, right? And the convergence in C0 tells me that I got away by a most epsilon, which is what I promised you in the theorem. So I stay close to the initial guy by epsilon. So I'm not going further away than epsilon. I want this one to converge, the series, right? Well, choose delta Q to be a geometric series, and then this guy will converge in C1. But if I choose delta Q and the thing is converging in C1, this is the error, somehow the error that I do in my equation, right? So how far is actually my metric to the target metric? And it's going to 0 pretty quickly. And so in the limit, my final guy is actually an isometric immersion. Okay, so, you fill in the details, but that's it. Now he spoiled the subsequent part of the movie, because exactly. So what if I want to have something which is better than C1? Okay. So now somehow in the back of say our mind, when Laszlo and I were thinking about this problem, we were just thinking like, okay, so first of all, we can try to. We have a convex integration scheme for L infinity Euler. There is a convex integration scheme for the Nash problem. I want to try a convex integration scheme like that, which is going to be C0 for the Euler problem. And so I want to actually construct continuous solution. But then I want to go further. Possibly I want to solve the conjecture of Onsager. So what happens if I try to construct somehow C0 alpha solution of Euler for a scheme that I have not yet invented? Well, first of all, I can try to understand what happens actually in the Nash scheme, right? If I actually can try to do a C1 alpha scheme. Okay, so here I'm going to have the discussion. So how about higher regularity? Well, of course, the first thing that you want to discuss is what happens to the second derivative, right? In principle, before I do the computation, I can't know why the second derivatives should go wrong. They should, huh? They have to go wrong. Because I have a theorem that tells me that I can't do that. The one that I gave you as an exercise with Gauss curvature. So it better be that the second derivatives are not converging, because if they are converging, then I find a contradiction in mathematics. And it's not like I'm using very fancy axioms, huh? So what happens to the second derivative? Well, you realize immediately that if I compute the second derivative of these guys, I have the second derivative of VQ. And then what do I have? Well, I have the things which I keep getting when I differentiate the fast cosines and sines, right? So I get a lambda times A times now, so there's a minus. So here there's going to be again a sine. and then I have my vector field n, and then there is minus lambda, and then there is the A, and then there is the cosine of whatever, and then there is the vector field B, and then I have everything else. Now, everything else doesn't get a lambda, so either doesn't get any lambda, is lambda to the power 0, or it gets a 1 over lambda, or it gets a 1 over lambda squared, right? I can try to make a Taylor expansion in lambda, in 1 over lambda. So of course, they are blowing up, right? Because these guys, they must be blowing up. How much are they, these guys? I mean, they are kind of lambda times delta Q to the 1/2. So this guy should better blow up. I should discover that this guy blows up, right? Which is not at all clear at the moment, because it's true, it's something which is blowing up, but it's multiplied by something which is kind of going down, right? Okay, so now, if the C2 norm blows up, I can still think anyway that more or less the estimate that I'm getting for the C2 norm is as good as it gets. It cannot be really much better than that. And so what about this guy over here, the C alpha norm? Let me actually write it in this way. So the C alpha semi-norm. I don't know if you're used somehow to this notation. It's like, you know, the part which you add to the C0 norm. So for a function f, it's going to be f of x plus y minus f of x divided by modulus of y to the power alpha, and then I take the supremum of that. So I mean, there's an important elementary inequality which tells you that this guy is less or equal than dvq plus 1 minus dvq in C0 to the power 1 minus alpha times d2vq plus 1 minus d2vq in C0 to the power alpha. And you see that you are getting a big advantage because the difference between these guys is vanishing, right? And this one is instead exploding. So the less, I mean, the smaller is alpha, the slower is this guy possibly exploding, okay? Okay, so let me try to understand which kind of C alpha norm I can make converge. And eventually understand also why certainly it cannot be the C2 norm. It will be some threshold which is intermediate between the C2 norm and the C1. Okay, in first approximation, let me do something which is certainly not true. Let me assume that instead of having to add all of these Nash spirals at each step, which was given by the geometric lemma, so that was m times m plus 1 divided by 2, let me assume I can add actually only one and be happy. It's not possible, okay? But let me assume I can. Of course, it's not possible with the spiral, but you don't know if you can actually devise some other mechanism that sort of adds all of the correction all together, but with a similar scheme, okay? Very well, so I'm going to assume then that VQ plus 1 is going to be equal to VQ, okay? And then there's going to be my lambda, and now I'm going to index my lambda by lambda q plus 1 because it's the next one guy that I'm adding, okay? And then I'm going to have the amplitude A, and then I'm going to have everything else over here. And the everything else is the cosine of the lambda times n, and then the sine of the lambda times b. Or maybe it's the sine plus the cosine, whatever. Okay, and remember, what is A? A is what we call delta Q. Okay, so then dvq plus 1 minus dvq is C0 is less than delta Q to the 1/2. Okay? That's what I have over here. Okay, dV, sorry, it's VQ. No, it's dVQ. Okay, and the second derivative because anything else, I'm hoping it's an error term, is going to be, and that's a constant. It's going to be less or equal than a constant, and then I have oh, sorry, let me call it delta Q plus 1. So let me see. I have, no, it's delta Q. It's the previous error. Yes. Okay, and this guy is going to be that 1. Okay. Okay, so it's only relabeling actually, but just because otherwise I get right. Otherwise I get very confused. Sorry. So it's only relabeling, but I mean, if you remember, we declared essentially delta Q to be the difference between the metric error and the target, right? So it was essentially this guy by definition. Now I should have known better. But you know, it's just a convention. Instead of calling it delta Q, let me call this guy delta Q plus 1. And the reason why I'm calling it delta Q plus 1 is that because then I have the same index between these two. Okay, it's only a relabeling. Now I have to be, in the previous iteration, really it didn't matter. Now it matters only for psychological reasons for me, because otherwise I'm going to make some mistake in the computation. Okay, so the C0 alpha norm is now less or equal than a constant, and I'm going to have delta Q plus 1 to the 1/2, and then I'm going to have lambda Q plus 1 to the power alpha, which shouldn't be surprising somehow. Like, you know, in Fourier, and this lambda is kind of the frequency. So in Fourier, the C1 norm is like the frequency, the C alpha norm is like the alpha power of the frequency. Okay? So I want this guy to converge. And let me from the start make an ansatz. I will make my lambda q's to be powers of some fixed frequency. So something times lambda to the power q. Okay? And I will make my delta q also powers of lambda, but with a different exponent. So lambda to the minus 2 alpha q. And of course, the larger I can make alpha, let me call it alpha 0. The larger I can make alpha 0, the bigger alpha I can beat over here to get something which converges. So this alpha 0 is the best alpha regularity that I can actually hope. So I will get Hoelder for every alpha less than alpha 0, depending on how big I can actually choose this alpha 0. You see what Ujwal was saying before, right? This one should be not too large in compared to the reciprocal of this other guy. Okay, because if this one is too large compared to 1 over delta q, this exponent has to be small. So, or maybe I don't get any exponent, right? It could even happen like that. Maybe I only have C0 convergence. So now, while before I was sloppy and I was choosing my lambda like huge, now I'm just going, wait a second. I don't want to take them actually that large. So what is the smallest lambda that I can choose in such a way that my algorithm is still giving what I want, okay? And let me not focus on this guy. Let me just claim that this guy is unimportant. Really what it matters is to actually get that the metric error is what I wanted, okay? So which one was good? The blue one. So let me go back and compute the metric error. Okay, so remember we had dvq, which is equal to, so dvq plus 1, which is equal to dvq, and then I have, you know, a cos, and then I have n tensor psi, and then I have a sine, and maybe I have a minus, b tensor psi, and here there are things which are unimportant. Okay, and then I have the ones in which I have the 1 over lambda q plus 1. Because I'm differentiating anything else. Okay, so for instance, I might be differentiating the A over here. And then here I would have like sine of whatever, and then I would have n. Okay, so what I really have is something like this. So n tensor gradient of A. Okay, so I will have error terms which are coming from cross products of many guys, right? Okay, so then I have another guy, for instance, which is this one. And so on. So I have many cross products, but just to kind of get a feeling for what I'm going to have, let me just say that I focus on the cross product of this guy with the largest that I have in here, which is this one, right? So this is of order 1. This is small, but this is of order 1. It's the derivative of VQ, which I only know it's going to be bounded by a constant because I'm converging in C1. So there's other things that I have to take. So I have to take like, you know, this guy times that guy, but it's certainly going to be smaller. But maybe this guy times that guy is worse. I'm not going to give you the computation. You just have to believe me that this one times that one is going to give me an estimate, which is like this one times that one, if not better. I don't remember. But this one is going to be the one which kind of bites me. Okay, so how large is this one times that one? So this one is a constant, and so it's really the size of this guy. Okay, what is the size of this guy? Well, this one I know, right? It's a delta q plus 1 to the 1/2. This one I know, it's lambda q plus 1. Okay, I have to understand what is the derivative of my normal component, right? It stands to reason that it should behave, if you don't choose your normal in a crazy way, it should behave like the second derivative of your function, right? Because there's the orthogonality condition. So try not to, you know, choose something which is spinning too much on the normal bundle. So you have something which is almost like the second derivative of VQ, okay? And we just said the second derivative of VQ, when I'm actually looking at how much it increments at each time, it's going to be delta q plus 1 to the 1/2 times, delta q to the 1/2 times lambda q times the frequency. So this piece comes from this guy, which I expect to be roughly like the second derivative of dq. Which, because I'm expecting that this guy explodes, it's geometrically, it's going to be as good as the next addition. Okay, so now this one has to be smaller than the next metric error, right? And I mean, in my iteration, the next metric error has to be delta q plus 2, okay? Because this is what I want. I mean, certainly I cannot be larger than this guy, right? In fact, I have to be smaller than a specific constant times that guy. Remember, I mean, the ball of radius C0 that we got from the geometric lemma. So this is a necessary condition that I have for my scheme to converge to what I want. Okay, so let's see what that gives, right? It gives a condition because our ansatz, okay, there's actually a constant over here that I want to beat. Now, the reason why I will be able to beat the constant is because I will not get really to alpha 0, like here. I will stay slightly below, and so there's a large power of lambda, there's a small power of lambda, but I can take lambda large to actually beat the constant, okay? So let me assume really I have alpha 0. So in here, I'm going to have lambda to the minus alpha 0 times q plus 1. In here, I have lambda to the minus alpha 0 times q. Then I have lambda to the power q. Then I divide and I have lambda to the power q plus 1. And then this one has to be less or equal than lambda to the minus 2 alpha 0 times q plus 2. Okay, now you take the logs, and it's a very simple computation. And the very simple computation gives you alpha 0 q minus alpha 0 minus alpha 0 q minus 1 less or equal than minus 2 alpha 0 q minus 4 alpha 0. And you see that these guys cancel. And you get alpha 0 is less or equal than 1 over 3. Okay. And this is a computation that, that Laszlo and I did together with Sergio Conti on this particular problem, in which we were trying to prove something, right? I mean, like, you know, the sort of best Hoelder exponent you can get for this scheme. Something which was done actually, so there was already a previous work by Borisov in the 50s, as I told you, 50s, 60s. So, and we were trying to understand that and improve upon that. And you can imagine that our mouth started watering, like, oh, what? It's exactly 1 over 3. How actually could that possibly happen, right? I mean, because it's exactly the Onsager exponent. So that's when we started believing that, okay, so first of all, you have to transfer to the Euler equations, and in the case that everything goes luckily, there is actually this exponent over there which is waiting for us, if everything goes well. So one first thing that you will notice immediately is that it doesn't go well, right? I mean, already for Nash, because this is not one step, I have actually to add many steps. So what happens if you have to add many steps? So let me go very quickly to this. So the multi-step. So in the multi-step, I need to choose a few lambdas before I actually get to my final guy, okay? So in the multi-step, I need to add a lambda q plus 1, 1, then a lambda q plus 1, 2, and so on. So this depends on which spiral I'm adding. Then there's going to be a lambda q plus 1, n. And then this one is really going to be the final guy, what I will call lambda q plus 1 without any index. Okay, and recursively, what is the C1 norm? Okay, that is of course always less or equal than delta Q plus 1 to the 1/2. And what is the C2 norm? That is always going to be something like delta Q plus 1 to the 1/2, and then there will be the final guy, right? Lambda Q plus 1 n, but it's exactly what I declared to be lambda Q plus 1. Okay, the first error is easy. So the metric errors that I do is, there is the first iteration, and it's going to be delta Q plus 1 to the 1/2, delta Q to the 1/2, lambda Q, and then I'm dividing by lambda Q plus 1, 1, right? Okay, but then there are the next terms, and in the next terms I have the next derivatives. And, okay, so who is the next guy? So the next guy is the second derivative of the first step, right? Of the first spiral. What is the second derivative of the first spiral? Is whatever I added, you know, whatever second derivative I had before plus what I've added actually over here. And what I've added over here is delta Q plus 1 to the 1/2 times lambda Q plus 1. So I have to replace this guy, which was the second derivative of VQ, with the second derivative of the first perturbation. So I'm going to have this one. Okay? And so on, until I arrive at the last one. And they all have to be less or equal than delta Q plus 2. So here's the condition that you have. You have this guy, which you already had before. Okay, and then you have these guys. And okay, it's not really the same as, you know, making all of these guys kind of smaller than that, but certainly if these inequalities are all true, their products are true too, okay? And if I make all the products, you see that I'm kind of eliminating these guys, right? So I will have lambda Q plus 1, 1 divided by lambda Q plus 1, 2, and so that one goes away. So certainly I need to satisfy this condition. Yes, this capital N is fixed. If you remember, it depended on how many spirals we needed to use, and it's the dimension of the symmetric matrices. Exactly. Yes. Yeah, so no, we can add them, sure. I mean, of course we can add them. I mean, but we want, I'm just going, you know, what is the best I can do? So certainly, if the sum is less or equal, each of them has to be less or equal. And if each of them is less or equal, then the product has also to be less or equal. Then, of course, to really show you that I can find, I mean, and I will find an abstraction. To really show you that I can actually find a system which is consistent, I will need to show you that there is a choice for which making the product wasn't a bad idea. For instance, because, you know, all of these terms, they contribute equally. And so if all of these terms, they contribute equally, whether I'm making the inequality for the product of them or the inequality for each of them is the same. That's what I wanted to say. So this is just telling you that you cannot do better than some alpha 0, but to actually get that alpha 0, you will need to sort of optimize the various errors. So they have to be all of the same scale, okay? So now multiply all of them, and you're ending up with the following inequality. Okay, and compute your alpha 0, and you will see that your alpha 0 has to be less than 1 over 2n plus 1, where n was the number of spirals that you have to add, and this is exactly 1 over m times m plus 1 plus 1. Okay? So, for instance, in dimension 2, the space of symmetric matrices has dimension 3, and you get 1 over 7. Now remember, if I could diagonalize in dimension 2, I would only have to actually add 2 guys. Can I diagonalize? Yes, in dimension 2 you can actually diagonalize, because there's the uniformization theorem, which tells you that you can put every metric into a kind of conformal to the Euclidean metric. So why actually is 1 over 5 a difficult theorem though? So this is a paper by Laszlo, myself, and a former student of mine who's called Dominic Inawan. Well, it's difficult because it's true that the metric error is small, but it gets higher and higher derivatives. And the conformal change of coordinates gets worse and worse. So it's not like I can simply change the coordinates conformally and think that everything is going fine. I actually need to write down estimates and see that the degeneration of my conformal change of coordinates is not actually messing up the estimates, okay? And in fact, for this reason, for instance, in that paper, if I remember correctly, we cannot go like with a geometric series like lambda to the power q. But there's another thing that should bother you. So down the line, at iteration number 1 million, each time I need to kind of, compute like second derivatives of the previous guy. But the previous guy depends on the derivative of the previous guy, right? I mean, every time that I write my formula for the function, the formula for the function has this one. And this one depends on the derivative of the previous guy. So when I'm actually computing a second derivative at step 1 million, if you go and trace back with the chain rule, there are 1 million plus 2 derivatives of the first step. So it's not really true that I can actually carry over these inductive estimates, because there's like, all of the past, which is kind of biting at me. Okay, so now you have two ways out of this. So what Borisov did back in the 60s, he just said, well, the heck with it. Let me start with a real analytic function, and so I know all the series. And I just simply keep all of the errors. Instead, what we do is something different. Instead of using exactly the previous map, we mollify it with a mollifier. And then we can estimate higher derivatives by like the first derivatives times the derivative of the mollifier. Of course, I will need to check that the mollification is sufficiently close to my original guy. Okay, which will mean that I will need some additional estimate with this modification. And I believe you kind of heard people in the previous lectures like talk about this kind of technical step in which you have to mollify. It's only a technical step, but it's important, because otherwise you have to go through kind of all of the chain rule and like account for infinitely many derivatives down the line for the first iteration, for the first guy, and for everybody that comes after it, which is a very cumbersome computation. Okay, so I'm extra time, sorry, but I'm ready to take any further question that you might have.
At some point you said that the difference of the q and in the derivative difference, you said you can relabel instead of delta q, you put delta q plus.
No, it's not the derivative difference, it's the metric error that I relabeled. Yes, it's the metric error.
Like relabeling, or so if I understand in terms of Euler,
yes.
So the derivative cost for the velocity,
yes,
is like lambda q delta q power half.
So for Euler is the size of the Reynolds stress.
Yeah, but Reynolds stress size would be really you need to be delta Q plus 1.
Yes, yes.
So it's not really like relabeling.
Okay, so it's not, okay, so it's relabeling in the following sense. That one is my next target, okay? And so I can call my next target delta Q plus 1. Then of course I have to make sure that my estimate gets me to the next target, okay? So in that sense, I could say it's just a relabeling. Okay, I mean, say that the next target that you wanted to shoot instead of being delta Q plus 1 was like delta Q plus 1,000,000. My estimate would still work. I just would need to actually get this error with, you know, here 1,000,000 and, you know, here whatever. So in that sense, I'm just giving a name to that guy. So let's say the metric error, I give it a name. And then I have the initial size of the V0, which are just constant. And then I start computing all the estimates by consistently with the name that I've given, because you know they depend on all the errors that I want to achieve. And the lambdas are instead parameters, really parameters which are like, you know, not depending on the others. But you are correct. I mean, once I decide that the label of the Reynolds stress is that one, my estimates have to be consistent with that label. But after I relabeled, I quickly went back and changed the estimates so that they are consistent. Okay, in that sense, it's a relabeling, sure. Yes. The starting one, yes. Yeah, that's what I would call, for instance, a subsolution. Is short, exactly. So. So one way to understand this is the following. So like, you know, my concept of subsolution, which should be the correct one, should allow me to move from the relaxation of the problem to the actual problem. So in the isometric embed, so like say, in the iconal equation, what is a reasonable notion of subsolution? Well, I should look at, you know, what happens if I take, say, a sequence of actual solutions and I take a weak limit. Of course, I'm going to have an inequality. It's a convexity inequality. If I take a sequence of isometric embeddings and I don't tell you anything, so they're not converging in C1, what is happening actually to the final guy? Well, the final guy could actually shorten lengths, right? I mean, because maybe my isometric embedding is sort of winding around. And so that's the notion of subsolution. And if you want, for Euler, it's the same. So when I put actually this additional Reynolds stress, and I look at the system that we call Euler-Reynolds system, actually Reynolds is just something, you know, the Reynolds stress is a name which existed before. We're just borrowing it from the literature. So you have to check what is the conditions that I have on that guy. And the condition that you have on that guy is some inequality, which comes again from some convexity consideration. And we saw it in the second lecture. I mean, you have to be in the convex hull of this particular K. Exactly. Yes. Yes.
There we were trying to also get some estimates about the N2 norms and things like that. There
yes.
I could see by using in the perturbation the sine and cosine kind of terms would make more sense.
Yes.
Here the domain is like a arbitrary kind of open set in some Rm. So
yeah.
Could you explain why?
Yeah, it's not necessarily, you don't have to take sines or cosines, and you don't have to take any particular frequencies, but you still want something which, you know, has a certain size in C0 norm, has a certain size in, you know, C1 norm, and has a certain size in C2 norm. So maybe you don't want sines and cosines, but you certainly want something which is localized in frequency in Fourier on some level. So it doesn't have to be e to the I n dot x. It could be more spread. And you essentially saw this in, you know, the previous lectures when you're trying to do kind of more complicated things. So, but okay, in this case, because sines and cosines work, we can just like stick to sines and cosines. In fact, when you're actually, for instance, doing the Kuiper, it's not even sines and cosines that you're using. You're still using periodic functions, but you're using periodic functions which are slightly more complicated, because you will not be able to kind of get the correction by squaring these guys. So you will need to oscillate in the orthogonal direction, but you will also need to oscillate a little bit in the tangential direction. So you will have a function which is oscillating in the tangential direction, just a tiny bit, and something which will be oscillating more in the orthogonal direction. And then you have to devise a correct function, which is not sine or cosine, to get actually your estimates. But there's a huge freedom. You still want something which is localized in frequency, though, because otherwise all of this kind of, thing is not going to be true. Yeah, sort of, yes, sort of. When you really get to the Onsager conjecture, then like everything will start looking a little bit like the scaling of turbulence. Yes. And of course, like, in the more sophisticated kind of iterations or arguments, the frequencies are kind of living all over the places. They are not anymore very confined, or like, as he was saying, as he was doing, for instance, you don't kill them, all of them at a single shot like we do over here and move immediately to the next frequency, but there's a much more complicated mechanisms that you can actually do.